Okay. Oh, where did my thing go? There it is. Okay. So y'all can go ahead and do attendance. Okay. We've still got a few minutes. How y'all like this weather? I'm loving it. I think it's awesome. It's finally not sweltering. How magical. Oh, I'm supposed to be monitoring the chat on my computer. I forgot about that. I'll put it on here for now. Getting close. What's that? All right, y'all want to hear a really bad third grade joke? Y'all, I was terrible. I got the Bad Mom Award yesterday. Yesterday was the first day, and I don't know how long, I forgot to put a joke in my kid's lunchbox. He did. He actually did. He didn't even say anything about it, which I was pretty impressed with. I thought I was going to get, Mom, you know, why didn't you? But then again, he doesn't like my jokes, so I don't know. But he was pretty excited. He needed one today. So today's is pretty third grade. So what is gray and goes round and round and round?
The moon.
An elephant on a carousel. Y'all know I make these jokes periodically, right? Okay. It's only me laughing at these jokes. It's only me. I make bad jokes periodically. All right. Has anybody been able to get a handheld eye clicker to work at home?
They don't work because you have to be close to the base.
You have to be close to the base. Okay. So Lillian, it is never going to work for you at home. So if you want to get the iClicker Reef app, that is the only way that you will be able to check in and get your participation points. If you have a handheld clicker and you are at home, you will have to get the app. Got one more minute. And don't forget to go ahead and do your attendance, check in on attendance.
The iClicker points. How are you going to add them? Like,
So at the end, it's a good question. At the end of the semester, I'm going to put a column in, like I would put an exam in, right? But that column is going to say iClicker points. It's going to be 150 points. So that's actually more than an exam. It's like an exam column. And it's going to be iClicker points, 150 points. So if you get between a 70, like when when you look at your app and it says like participation and attendance. Ooh, did my mic go out? That's not good. Okay, we're back. All right, y'all tell me if it happens again. So at the end, I'll put the column in. Then you go in the iClicker app and you look at your score. There's participation, there's attendance, and then there is performance, right? So I'm looking at performance. If you have between a 70 and 100%, when the end of the semester gets here, that'll be 150 out of 150 points. So that can really, really, really help you out. But you only need to get a 70% to get a perfect score. Right? So the more you participate and the more you try and the more you have watched the lectures before you come to class, I want to say lecture again, the better prepared you're going to be. Does that make sense? Performance. So maybe it's score. I mean, it depends on what you see versus what I see. So I think score and performance are the same thing. Somebody's got a question to that? Not till later because they're going to constantly change.
no, I just want to make sure it's like.
Yeah, you're going to get, I promise you, it's in the syllabus. You are going to get 150 points for your iClicker participation. Absolutely. So there's no bonus in this class, but there's that at the end of the semester, right? But the point is, don't ignore doing the iClicker because it's going to help you. But if you don't do it, it's going to hurt you, right? So be careful.
So our exams are out of 100 on the calculate our grades, but they're out of 120 on.
Wait, say that again?
Our exams out of 100 on.
Your exams are out of 100.
But on our exams, they're 120 points a piece.
No, is this class 100 or is this class 120? I did my classes differently. I don't remember. Hold on. Let me look on. I don't remember what I did for my different classes, so I don't want to say the wrong thing. Oop, that's not the right one. Okay, so Holly, can y'all hear me at home?
I see what you mean. On the syllabus, it shows 100 points each, and then on Moodle, they come up as 120.
As 120?
So that average is going to be different, right?
Yeah. Is it? It should be whatever it is on the syllabus, but I might have mistakenly put it as one or the other. Regular exams, 100. Okay, so I'll go back and fix that on Moodle. I'll go back and fix that. And first you have to, I can hear you. Yep. Okay. So y'all got that? I'll go back and fix it. I'll go back and fix it.
So an average is correct for Moodle, though, right?
No, because it's going to change to 100. There's supposed to be 100 points, not 120 points. If you do your homework, it's going to help you. Yeah. So just y'all, I will go back and fix it tonight. It'll be right tomorrow, okay? So just relax. Good? It would actually improve your grade. It will actually improve your grade. Well, depends, but for most of you, it will probably improve your grade. Okay. All right, so last time we had an exam. So I want to start off today with a little reminder about what we should be working on right now. So last time we had regular lecture, the day before the exam, the class period before the exam, we did the first half of chapter 5. So today we're going to do the second half of chapter 5. But I thought it might be a nice refresher to do clicker questions on the first section. Yeah? It's kind of a refresher, and it should be pretty helpful. All right, so if you have an energy diagram of a reaction and the products are shown at a higher level than the reactants, what must be true about this reaction? So if you have an energy diagram and the products are shown at a higher level than the reactants, what must be true? Draw your little energy diagram if you need to. I think it helps to draw it. And remember what an energy diagram is. That's just looking at the top of my head. Okay, I'll give y'all about another 20 seconds. Okay. All right, so if we have an energy diagram, what does an energy diagram generally look like? Maybe. I'm trying to write. Oh, y'all, really? No, what are you doing? This is not good. Will it write on anything? Let's see. No. All right, I'm going to try and fix the board. Hang on, y'all. not my day, y'all. Won't even let me orient the board. I'm pressing the center of the target. Try that again. But you gotta give me another one. No, I really don't want to restart the computer. Oh, I got the little pin. It'll say it's changing color, but it won't draw. Oh, really? No, I can do. Well, okay, so that'll work. All right. It's not what I want to do. Okay, so all right. So in our energy diagram, right, our products are shown at a higher level. If our products are up here and our reactants are all the way down here, right, what must be true about this reaction? That the reaction must absorb energy from the products. So if you're starting out with something that's low energy, how are you going to end up with something that is high energy? You're going to have to get that energy from somewhere, right? So the reaction is going to absorb energy in order to form the products. It has to increase its energy. Exothermic would be the opposite, right? It would release energy. Okay. Delta H is less than 0. Could we say that? What is H? Enthalpy, right? Okay, so we're not talking about enthalpy. Can we talk about the potential energy? No, we can't really talk about potential energy. The products are more stable than the reactants. No, this is actually the reverse, right? It's really the reactants that are more stable than the products. So the last option is backwards, okay? All right, let's see. See if I can make this go without using the pen. All right. Select the correct statement regarding the reactions represented by our two energy diagrams. So you have to compare A to B. When you're looking at your options, compare A to B. Is it working for you now?
Yeah, there's another person that didn't work. It came with like a bullet symbol.
Okay. All right, I'll give y'all another 10 seconds. Do y'all need like a minute 30 to answer? You think a minute's still good? Minute 30? Okay. All right. Okay, so what can we say? Reaction A is exothermic. What does exothermic mean? Exo means it's going to exit. So which one is energy exiting the reaction? Neither one, neither one. Okay, reaction A is slower. Yes, why can we say reaction A is slower? That's true. The activation energy is lower. So here's the peak, right? So this reaction had to go from all the way down here to get all the way to the top of this peak. Whereas this B reaction went from here to here. So there was less energy to overcome. So B is going to go faster or A is going to go slower, however you want to think about that. But either A is slower or B is faster. Okay, B is exothermic. We said neither one is exothermic, so that's wrong. B is slower, and we said no, it's the opposite. And both reactions are equally fast, and we said no, that A has to be slower. Okay. And I graded that one, yeah, okay. Okay. All right, so this one, you're gonna have to do a little math, so get out your calculators. Get out your calculators. Maybe a scratch sheet of paper. Okay. All right, so we have a food label, and I'll give you all some extra time on this one. And it lists the following: 22 grams of carbohydrates, 7 grams of fat, 5 grams of protein. How many calories are present from carbohydrates? Be careful with that. How many calories are present from carbohydrates? I'll give y'all 2 minutes. Yeah, make sure your masks are on. Okay, 10 seconds. Help us in. No, we had like 80 people. All right, so when you were looking at this problem, what did you really need to only look at? The carbs. Oh, and now my little pen went away. Yeah. Not my day. So you looked at the carbs, right? And so when you looked at the carbs, here 22 grams of carbs, how do I know how many calories are from the carbs? I need to know my conversion right here. So I need to know how many calories I get per gram of carb, and I know that I get 4 calories per gram of carb. So 22 times 4 should give me 88. So it should be B. Good. All right. Activation energy. So this is a basic definition one. I want to know, what is the technical definition for activation energy? I'll give y'all a minute 30. And while y'all are working on that, I'm going to try and get the pen to work again. trying to get all the technology to go. Okay, that's 1:30, so y'all please weigh in. All right, so what did you say activation energy is? Activation energy, y'all did pretty good. Y'all did pretty good. All right, is it high in reactions that progress slowly? Yeah, that's what we saw in that first diagram, right? We had a big mountain to climb in order to get to our products. So that one's true. Are they affected by the presence of a catalyst? Yes. How does an enzyme, how does a catalyst change that reaction diagram? But how does it speed up the reaction? I'm gonna draw this. By lowering the activation energy. Oh, I'm like the space for this mouse is about 2 inches large. And I don't even know how to erase. So I'm just gonna try again. Okay, so here's my diagram, right? If I have this similar curve that I had before, right? I'm trying to get from reactants to products. How's it gonna be different if I have a catalyst? Am I gonna start at the same place? Yeah, am I gonna end at the same place? Yeah, what's gonna be different? I'm not gonna have as big of a mountain to climb, right? So it's like the catalyst is stepping on that hill and making that hill smaller. So the smaller the hill you have to climb, the easier it's gonna be for the reaction to go. So activation energy is affected by the presence of a catalyst. The difference in energy between the reactants and the highest point on the energy diagram. If here is our reactants, here's our highest point on the energy diagram. That is our activation energy, right? And if you had a reaction that was going this way, right? The same is true. Here's our reactants and here's the highest point. This is our activation energy, right? Okay, so that's true. The amount of energy that must be attained by reactants for a chemical reaction to occur. And that's true. This is really the definition. D is really the definition. All the others are also accurate. Okay. All right, so that is our little review. And now what I want to do is, I am dreading this now that my thing won't work. I'm going to try and close the Smart Notebook, all the Smart Notebook stuff, and try and open it up again. And we're going to cross our fingers that that makes it work, because I'm really dreading writing with the mouse all class period. Okay, so we already started working on this, right? Hello, let's see if this works. Okay, I think we ended on section 5.3, right? Last time we ended on 5.3. Like we didn't start 5.3. We did 5.1, we did 5.2, and now we're on 5.3, correct? Yeah, everybody with me? Okay. What? 5.20, right? Okay, so now we're on 5.22 because I did 5.21 in the video. All right, so categorize. Let me do this full screen. Do I still get my pen? No. Where did my pen go? Let's try this. Oh. Is it Monday? Because it feels like Monday now. Categorize the following reactions as synthesis, decomposition, or exchange. Okay, I'm going to tell you this, and I'm going to tell you this on like every single chapter. If you're reading the directions and you don't know what the words mean, you're going to have a really hard time doing the problems, right? So my suggestion is when you read the instructions to help yourself to start to study, you write down, okay, what is synthesis, right? How could I write a general reaction for synthesis? It could be like A plus B goes to what? AB. Oh, this is torture for everyone, for y'all, for me, this is torture. All right, so how about decomposition? AB goes to A plus B. So it's really just the opposite, right? Synthesis and decomposition are opposites of one another. Now, how about exchange? There are two different ways that you could have an exchange reaction. You know what those two ways are? You could have AB plus something else, plus C. What would my products be? AC plus B. Now there's another way that this could happen. AB plus what? CD. Okay, now we're going to exchange them, right? Okay, so remember that you have usually a non-metal and you usually have a metal and a non-metal, a metal and a non-metal. So you're going to exchange B and D, right? Or you could say you're exchanging C and A, but you always have to exchange the first ones or the last ones, but you can't do like AC and BD. Well, you can't, yeah. So what do you get? You're going to get AD plus B plus, no, CB. Yes, that's my son's initials, CB. Okay. Yeah? Correct, because this would be like sodium chloride, NaCl, plus potassium chloride. Potassium, we'll not say chloride, we'll say potassium fluoride, right? So sodium and potassium are both metals. So you're not going to get a metal bonded to a metal. What are you going to get, right? So if you actually put things in place there, it kind of makes sense as to why. Because you're not going to have chlorine and fluorine unless you have a covalent compound, right? Okay. All right, so when we look at A, what's the general format? It's synthesis because we have one thing, we're adding it to another, and we get one product. So this one, I'm just going to write an S, must be synthesis. Y'all will forgive me today, right? Okay. Oh, and I just kind of drew on things. How do I do this? There must be an eraser. Oh, that's a good idea. Okay, that's a great idea. Oh, y'all save me every time. So this one was synthesis. Okay, so how about B? B, we're going to have exchange. B, we're going to have exchange. It's right. What type of exchange is this? This is a particular kind. I see a hydrocarbon and I've got oxygen. I'm going to slam my oxygen into my hydrocarbon and I'm going to make carbon dioxide and water. What kind of a reaction is that specifically? That is combustion. Oh my goodness. Combustion, C-O-M-B, combustion. B, not a P. Okay, so that COM stands for combustion. Today's a holiday. All right, how about C? We have two things together and two things together, making two products. And what happened to those products? We swapped them. We swapped the SO4 and the OH, right? Because now we have potassium with our SO4 and we have aluminum with our hydroxide, right? So what do we call this? Exchange. Good. Okay, so now we're going to look at a reaction and we're going to determine, is it reversible or irreversible? So what could I write on top of these two to help me to remember that? I know it seems silly, but if you kind of get in the habit, it's going to work. So what would I write if I want it to be reversible? What's an indicator that this reaction, any reaction, is reversible? The little double arrow. The reversible reaction sign, reversible yield sign. So irreversible is the normal yield sign that y'all are comfortable with, right? Reversible, it's just saying it's going in both directions, right? Okay, so in A, what do we get? Reversible, we see that double-sided arrow. In B, irreversible. Now, even if they didn't have that there, what kind of a reaction is B? Combustion. Are you going to combust anything and be able to go back? No, you just exploded it. You're done. It's vaporized. It's in the atmosphere. You're not getting the pieces back. You need to move on. It is irreversible. Okay, how about C? Irreversible. Okay. All right, now we're going to talk about balancing equations, but we're balancing combustion. And I'm showing you this one just as a reminder that whenever we balance a combustion equation, you should be able to, number one, recognize that it is combustion. How do I know that this is combustion? We have a hydrocarbon, which is hydrogen and carbon only, and we're adding it to oxygen. So no matter what combustion reaction I have, what are my products going to be? Water and carbon dioxide. My advice to you is to balance your elements in this order: carbon, hydrogen, then oxygen. So remember that when you're balancing combustion reactions, you want to balance in the order of CHO. And a lot of times what you're going to have to do is multiply by 2 because this is always going to be an even number. And so I'll show you. Oh, I really don't want to balance this with this pen. I'm going to give it a go though. All right. So we're going to make what? Water and what else? CO2. Okay, so what's our order? CHO, right? CHO, CHO. That's the order we're going to go in. All right, so let's do our carbons first. How many carbons on this side? 4 carbons on this side. How many carbons on this side? Only 1. So what do I want to do? I'm going to put a 4. So now I can put my carbons and I'm going to put 4. I'm trying to skip a few steps. I apologize, but so I don't have to write quite so much. All right, what's my next element? Hydrogen. I want to balance my hydrogen. Okay, so how many do I have on this side? I have 10. Okay, now be careful when you come over here. How many do you have? 4 times 2 is hydrogen. Sorry, y'all. Whew. How many hydrogens do you have? 2. All right. So what do we want to do to our hydrogen? We want to put a 5 in front. So now I have 5 times 2. That gives me 10. Okay, now what am I going to do? Let me extend this page. Maybe I can. Okay. So now what am I going to do? I want to check on my oxygen. So how many do I have over here? 2. How many do I have over here? Now, 4 times 2 is 8 plus 5 is, yeah, so is that going to work? No, it's really not going to work. So what I really need to do is I need to, before I balance, just multiply everything times 2, right? Okay, so how does that change all of my stuff? I really would love to write in a different color, but. Okay, so I would get a 2 here, right? Now, do your other ones. Don't do oxygen, right? Do everything else. So instead of 5, what do I want instead of 5? I want 10, okay? Do the same thing over here. Instead of 4, I'm going to want 4 times 2 is 8. Oh, 8s are hard. All right, now, instead of having 4, I have 8. Instead of having 10, I have how many? 16. Let's make sure we're still balanced on the other side. Instead of having 4, I have 8. Oh, I have 8. I don't know what that is. Okay, and then my hydrogen, instead of having 10, I have. But how many hydrogens? Let's see, 2 times 20. Ooh, y'all, 20. I'm looking at. Wait, no, you have 20. Yeah, you have 20. 20. Try to squeeze that in there. 20. Okay. Hydrogens, 2 times 10, you have 20. Okay, now let's look at our oxygens. What do we have? Oxygen, 10 times 1 is 10. 8 times 2 is 16. So what do we have? Okay, what times 2 is 26? 13. So if I put a 13 right there, 13 times 2 gives me, I look like I'm drawing like a 3rd grader, 26. I think actually my 3rd grade son writes better than this. I'm so sorry. Okay, so we all right on this one? Questions? All right. Okay. So this one, let's review 27 before we answer 28. All right, so 27 said list similarities between chemical equations used in organic and chemical equations used in biochemistry. So this is similarities. If we're going to show an organic chemistry reaction and we're going to show a biochemistry reaction, we want to look at the structure. Because a lot of times, what's changing isn't really the molecular formula, but it's really the structure, right? You might have the same number of carbons in the molecule, but it's in a different arrangement, and that's very, very significant. So we're always going to show the structure. We're going to look at our yield arrow to tell if it's reversible. That's true for both of them. And so because the structure is shown, we're going to see those changes in the structure, and we're going to see the changes in the functional groups, right? And we're also you're going to balance both of them, right? We're going to make sure they're balanced. Now, let's do the difference. So I'll just put the difference between chemical equations and organic equations. So general equations, how do we write a general equation? Right? Remember our like A plus B, I'm not gonna write it, that'll take forever. And A plus B, was I writing the structure of A and B? No, but what do I have to do for organic equations? I have to show structure. So do we show structure in chemical equations? No. Here we're just going to give the molecular formula. The molecular formula. What do we give over here? We give a structural formula. All right, is that our only difference? Sometimes you do. Sometimes you do. So sometimes you, whether it's an organic reaction or a chemical reaction, you do have to look for that. So you have to identify, is it reversible? Is it non-reversible? And you can do that with the arrow. So while you can balance both of these equations, balancing an organic equation is not that important. It does happen. It is balanced. There is a conservation of matter, and so you can balance it. But a lot of times, we don't care if we balance it or not. What are we really worried about in an organic equation? Somebody, I heard. What's it turning into? What's the structure of the product, right? So we don't care so much about balancing as we do about structure. So an organic chemical equation is all about structure. In a general chemical equation, if all we're worried about is the molecular formula, then it's very easy to balance. But in organic, I don't want to say we don't care, but it's not as important, okay? So you can write that. It's not as important to balance. So not as IMPT. To balance. Oh, this is terrible. To balance. All right. Now for the good stuff, right? Oxidation reduction reactions. So tell me about oxidation reduction reactions. There's a little thing, if I want to know if something's undergoing oxidation or reduction, there's a little thing I like to use. A little mnemonic. What's that little mnemonic? Oil rig. Look, that's perfect for us in South Louisiana, right? Oil rig. Now the question is, do you know what oil rig means? Oxidation is losing or is loss of electrons. So I want you to make sure to put that little E in. So what does rig mean? Reduction is gain of electrons. So let's do A. Copper 2 ions in solution. How would I write that? Copper 2 ions. What's the symbol for copper? I did this one in the video? Oh, okay. All right. Sorry, y'all. I guess I must have made this before I made the video. Oh. Okay, so remember oil rig. All right. Thank y'all for saying something. All right. A, silver ions are electroplated as silver atoms on flatware. So how would I write the abbreviation for silver ions? Ag, and it's given to me there, Ag plus, okay? And now, what are they turning into? The neutral atom, right? Because there's a difference. When we say ion, that's charged. When we say atom, that's neutral. So we just do this, Ag. And a lot of times, those are solid, right? They're plated. So it's solid so that you know that solids have a charge of 0. So what did we do? We went from a charge of +1 to a charge of what? 0. How did we do that? We gained how many electrons? 1 electron. How do we know that? Well, if you do +1 -1, what do you get? 0. Okay, so tell me again, what's a gain of electrons? That is reduction.
Would we always be given Ag plus? Or we would have to realize the plus one?
You might have to, for certain elements, you would be given it. That's a transition metal. So I'm not gonna make you know the charge on transition metals. But if it's one of the ions that's in the main group elements, then yes. Yeah. Okay, D-glucose reacts with hydrogen to form sugar alcohol D-sorbitol. Oh my gosh, that was a lot of information, right? So how are we going to answer this one? You what? So the other thing, and I had it in here, let me see if I want to show y'all something, and I want you to write this down. So this is from our lecture. There was something I had in there that was a nice little shorthand for all this oxidation reduction stuff. Let me come down. Nope. I had it in there. Okay, this right here. So you see this? Oil rig only gives you half of the types of oxidation, the ways to recognize an oxidation reduction reaction. Here's the rest. I wonder if I can copy this. Let me see. Let's stick it in there. No, I can't. Okay, so what you have to kind of just remember, right? Let's see if I can do this. Y'all, today is just not my day. Come on. Okay. So we'll put it right there. All right, so D-glucose reacts with hydrogen to form the sugar alcohol D-sorbitol. So what it's basically saying is you have something and you're adding hydrogen and you're getting something new. So we're going to call it Y, right? So is this oxidation or reduction? Are you gaining a hydrogen or are you losing a hydrogen? You're gaining a hydrogen, so this must be reduction. So it's reduction because we are gaining our hydrogen. I'm telling you, you need to write this down. You need to use this. You need to know this, okay? This is gonna help you out so much. All right, C, let me draw a line. C, the biomolecule FADH2 loses hydrogen, becoming FAD. If you are losing hydrogen, which one are you? Oxidation. Okay. All right, so I did 5.31 in the video, right? All right, although we mine most sodium chloride, it can be synthesized by the reaction shown. Identify the reactant oxidized and the reactant reduced. Okay. So what you need to do is you need to look at the different parts of this equation and see what's happening. Let's look at sodium first. Okay. What is it in the reactants? What charge? Positive what? Is it? It's 0. Why is it 0? It's a solid, so be careful with that. Be very, very careful. Okay, so sodium goes from a 0. Now, we know this total ionic compound must equal to 0, but that's the sodium plus the chlorine, right? So sodium plus chlorine equals to 0, but what is sodium all by itself? How do we do this? If we know it's Na1, Cl1, what do you do with these ones? You cross them. So you do kind of the reverse. So chlorine is a -1, sodium -1, +1. Thank you. Right? And you can go double check that on the periodic table, because sometimes you had to reduce to get this equation right, but a lot of times you can just do the reverse crisscross. But if you're ever, I don't know if that's right, go check the periodic table. So what did your sodium become? +1. Okay, so what did it do? It lost, oh my goodness, it lost an electron. So if it loses an electron, what do you have to be? Oxidation. Okay, let's do our chlorine. I mean, it has to be the other one, but let's make sure. Chlorine. What are we to start with? All of our diatomic molecules, so if it's two atoms of the same thing and they're covalently linked together, they have a charge of 0. So that chlorine is going to go from also a charge of 0 to a charge of what? -1. What did it do? Gained. And we already knew this. We're just putting a different definition to it, right? Y'all told me that when you form an ionic compound, what happens? One's going to lose an electron, the other's going to gain an electron. Y'all already knew that. We're just thinking about it a little bit differently today. Okay, so what are we? Reduction. Yeah? A lot of people hear oxidation reduction and they kind of freak out, but it's not bad as long as, if you can get this, you've got it. You've got no problems. All right, let's see. Can I get it back here? All right. So which one we doing? We're doing even. Woo. All right, let me extend the page. Too much technology on my screen. All right. So we have ketone bodies are molecules that are formed in the liver during periods when carbohydrate intake is restricted. Acetoacetate and beta hydroxybutyrate can be converted into energy in the absence of glucose. The two molecules are interconverted through the redox reaction shown. What's a redox reaction? Oxidation reduction. It's just a short way to say it. Identify the reactant oxidized and the reactant reduced. Okay, so what are we going to do? What? Yep, so we want to look, in this case, we're not necessarily looking at electrons, right? If you're looking at ionic compounds, we know electrons move, and it's very easy to track that. But with these kind of equations, it's a whole lot easier to track our hydrogens and our oxygens, right? So there's one, to me, that stands out that's super, super easy to recognize. Something to do with hydrogens. Do you see it? What happened here? Our NAD gained hydrogens in order to become NADH, right? So we went from NAD plus to what? Oh my goodness, y'all. NADH. So what happened in this reaction? What happened to my hydrogen? Did I gain or lose? I gained, I'm just going to put a G. I gained a hydrogen, right? What does gaining a hydrogen mean? Gain a hydrogen means reduction. Okay. Now, by default, your other substance has to be the reduction, but how can we prove that? What are we going to look at? Two molecules, oxygens and hydrogens. Let's look at our oxygens first. Here's one oxygen, 2, 3 oxygens. How many oxygens are over here? 1, 2, 3. Okay, what else can we look at? Hydrogens. We got 1, 3, 6, 7. How many do we have over here? 3, 5. What happened? We went from beta hydroxybutyrate to acetoacetate. We lost hydrogens. We went from 7 hydrogens to 5 hydrogens. So if we lost hydrogens, what's a loss of hydrogen? Oxidation. So this is our oxidized reactant. OX. Dang it. Oxidized reagent.
So the reason why we stretch out, like on the last one, after the oxygen, the water, the carbon, and the oxygen.
Wait, which one I crossed out?
On that one.
On here?
The previous one,
Right, so you're checking for oxygens or you're checking for hydrogens. Either one. So it doesn't matter which one you start with. Sometimes you'll see oxygens change, sometimes you'll see hydrogens change. Sometimes it's easier to count oxygens because there are fewer of them, right? They got hydrogens hooked to all the carbons. So you end up counting a lot. But what you could do if you want to cut down on that counting is that I could look here and I could say, okay, I have a CH2. I could get rid of my CH2, right? I have a CH3 and a CH3. Okay, I can get rid of that, right? And then here what I'm left with is 1, 2 hydrogens and none. So it's still a reduction of 2 hydrogens. That's what you're asking?
I was just wondering how
More than one way to skin a cat. I love cats. I don't know why I say that so often, but I do. But I love cats. Don't get me wrong. All right, we good? All right. Okay, 5.5, condensation and hydrolysis. All right, what do we say you should think about when you hear the word condensation? You have your glass of water and you put it on the counter, right? Your nice glass of iced tea or iced water, whatever it is. And what happens when condensation occurs? Water forms on the outside of that glass. So if you are going to form water, right, that's going to be a condensation. Tell me about hydrolysis. What does hydro refer to? Hydrogen. And what about lysis? You're what? You're breaking it, okay? So read the words and think about those connotations when you're trying to go through these problems. Okay, so in the video, man, I'm not hitting on all cylinders today. In the video, I did the odd numbers, right? Okay, so the even. What type of chemical reaction is condensation? Synthesis, decomposition, or exchange? You just told me condensation is what? Formation. You end up formation of water, right? So what kind of a reaction is that? So this is like one of the products. You get something else and you get water. So what do you get? You get synthesis. You get synthesis. So what's my general equation? I have some kind of a molecule in condensation and it's attached to an alcohol or a hydroxyl group, whatever you want to call it, right? Then I have another one and it's some other molecule. And it also has this hydroxyl group. That is supposed to be a 0 or an O, sorry. Right? So what's going to happen? What's my other product? I'm going to form water. That's true. And what else? You're going to pick one of these oxygens. And this oxygen is now going to go over and create a bond with this R group. What's going to be left over is a hydrogen, and an oxygen. What's another way to write hydrogen, hydrogen, oxygen? H2O, right? Okay, so what are we going to make? We're going to make R, we're going to make O, and we're going to make R. right? Okay, so we are synthesizing new products with this. So this is synthesis. All right, let's see. Draw the products formed from the ester. I guess I could do this full screen now, huh? Okay. Draw the products formed from the ester hydrolysis reaction shown. Okay. So what am I going to do with? This is hydrolysis, so it's not hydrolysis, it's hydrolysis. What's the difference between hydrolysis and what did I say? What's the difference between hydrolysis and hydrolysis? What are we going to do? If this is HOH, what's going to happen? We're going to break it up. We're going to break it up right there. Okay? So where's that going to go? Like, okay, I know I'm going to break it, but how do I predict the products from this? What was my general? Do you remember I had something that looked like this? Remember this? Right? And I had water. These were my products earlier, right? Now, what if I put this reaction going the opposite direction? What's going to happen? Right, so then I'm going to make my, I'll move this over. I'm going to make my ROH plus HOR, right? So where's the oxygen that's between these two R groups right here in this molecule? This one right here. It's linking two halves of the molecule. Could it be this one? It's not linking two halves, right? I need to be able to break a bond and end up with part of the molecule on one side, part of the molecule on the other side. If I break the bond here, all I'm going to be left with is a free oxygen. So I can't do that, right? So let's break it right here. So what am I going to end up with? So just copy what's here, H3C. Then we have an oxygen. And what's that oxygen going to get? A hydrogen. Okay, now you got to stop because that's the break. Oh, come on. Let's do that again. Okay. So you got to stop there, and now we need our other product. Now, we took this hydrogen and we stuck it right there. So where is this oxygen and hydrogen going to go? Right here, and it's going to bind to this carbon. Okay? So what are you going to end up with? A hydrogen and an oxygen. That's what came from water. And that's bound to what? Carbon. And now you just rewrite the rest of your molecule. Okay? Not so bad, right? You just got to know where to break it. If you know where to break it, you'll be okay. And then you give the fraction of the molecule that got the oxygen, you give it one hydrogen, and the other fraction of the molecule that didn't get the oxygen, you give it both oxygen and hydrogen. So they both end up with a hydroxyl group on the end. Okay? All right, so we did that in the video. All right, write the products for the following hydrogenation reaction. And I think I apologized on the video because this stuff was supposed to be over there. But so what we'll just do is we'll put our products here so that usually they go over here, but this is absolutely not enough room. So we're just going to put them over here. All right, so write the products for the following hydrogenation reactions. Oh, what are we going to do for this? Hydrogenation, we should add H2. Okay, so where's that H2 going to go? What's up with that? How do we know what's going to happen in a hydrogenation reaction? What's common in all of these reactants? A carbon-carbon double bond. So you will have a carbon double bound to a carbon, and that is what you are adding this H2 to. Okay? So each of these carbons is going to get one hydrogen. So that one gets a hydrogen, and that one gets a hydrogen. It's like Oprah. You get a hydrogen, you get a hydrogen, right? Everybody gets a hydrogen. That's hydrogenation. Okay, so I'm going to write my carbon, right? And now, if I add a hydrogen right here, what happens to this double bond? It becomes a single bond because I added one there and I add one here. So you got to basically get rid of this double bond and you end up with just a single bond. So my two carbons in the middle end up looking like this, and then I'm just going to put an R, and that R is all of this, okay? It's going to have a hydrogen and another hydrogen, right? Now, how about this carbon over here? We give it its original hydrogen, we give it its new hydrogen, and then we're going to give it all of this stuff that was there to begin with. And I'm just going to put an R because we would be here all day. Does each carbon have a complete octet? Absolutely. 2, 4, 6, 8. So the molecule is stable. If you looked over here, right? 2, 4, 6, 8 originally, but when you add that extra hydrogen, you got to make sure to take away that double bond. So just be very careful about that. I love this when they give us skeletal diagrams because they are so easy to do for a hydrogenation reaction. We look at the carbon-carbon double bond, and we're going to add hydrogens, right? I'm going to add hydrogens, but when we draw a skeletal diagram, do we include these hydrogens? No, so what do you have to do? Just redraw it, but take away. So let's see. I have 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8 carbons. And coming off of carbon 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I have a methyl group.
So when you would redraw that one, you wouldn't make it straight
Since it's a single bond. So if you only have 3, it's no longer trigonal anymore. It's trigonal planar. It's no longer tetrahedral. It's trigonal planar. And so it has a different 3-dimensional conformation, which is why they draw it straight. But this is the structure for a saturated hydrocarbon. So, yeah. So all I do is count my carbons and then redraw it. Good to go. How about this one? What do? Add our hydrogens, right? 1 to each carbon that participates in the double bond. But do we include that in our structure? No, it's a skeletal diagram, so we don't have to include it. This is super easy, right? Just draw this one to me I always say looks like a house. A terrible, sad looking house today. But it's the same thing, except it does not have this double bond. It's a sad one. It's a very sad, sad house. Okay? So hydronation is just adding our H2, 1 to each carbon on the carbon-carbon double bond. All right, so now we're going to hydrate our alkenes. We're going to hydrate our alkenes. How are we going to hydrate alkenes? What do we want to do? I'm so dehydrated. What do I need? Give it water. Give it water. Y'all are gonna think you're gonna sit on the exam, you're gonna read hydration, and then you're just gonna think of me up here dying of thirst because I can't have a drink of water while I teach because I have to wear a shield and a mask and all that, right? So think, if you're dehydrated, you need to add water. So if you're gonna hydrate someone, you give them water. Okay. All right, so, wait, I'm doing the wrong one. Right? Did I skip? Did I skip one? Did I just copy and paste? It's a struggle today. Did I copy and paste the same one? 39 is hydronation. This should be hydration. I think I put the wrong picture in. Y'all, I must have put the wrong picture in. Because it should have been hydration. Oh. But you don't have to worry about this, right? You're not going to worry about this. Right? Because it was the same ones that were in 5.40. That's my thing. I just should not have added that. Right? So we have the same alkene here, but now we're going to hydrate it instead of adding H2. So if we do this and we add water, right? I could do this. Okay, so what are we going to do? In this case, we have 3 atoms inside of our water. So what's the problem? We can't give each equal things, right? So H2O is really HOH. So one part of this molecule is going to get a hydrogen, the other is going to get the hydroxyl. How do I know which one's going to get what? Remember there was a little rule? Hydrogen likes to hang out with hydrogen. Hydrogen likes to hang out with hydrogen. So whichever one has the most amount of hydrogens attached to it, that's the one that you give just the hydrogen, and then you give the other one the OH. Okay? Yes? No? So one of these carbons is going to get a hydrogen, one of these is going to get a hydroxyl. So which one do we give? How many carbons are over here? 1, 2, 3. How many carbons are over here? 1, 2, 3. So does it matter which one you do for this one? Does not make a difference at all. So just give one side the OH, give the other side the hydrogen, and remove that double bond. Okay? So then your product would be carbon, carbon, and I'm just going to draw this as an R group. Oh, I don't really want that to come up. That's an R group. Kind of ignore that. This one's going to have the hydroxyl, and this one's going to have the hydrogen, right? And then over here, you'll have your hydrogen. Here's your new hydrogen. And then here is your R group. Okay? Hydrogen likes to stay with hydrogen. So whichever side has more hydrogens, that's what you're going to put it with. We'll see some examples where we'll have to do that. All right, let's do this one. So here's my carbon-carbon double bond. So here's the carbon I want to add to, and here's a carbon I want to add to. One of them is going to get the hydrogen, one of them is going to get the hydroxyl. The left side is going to get the hydrogen, because if I look here, I have carbon here and I have carbon here. So I have 2 carbon groups. I have a long chain and a short chain attached to my carbon. Here, what do I have? A shorter chain, right? So I only have 1 carbon group attached here, whereas here I have 1, 2 carbon groups. So where am I going to stick my hydrogen? I'm going to stick my hydrogen on this one, and I'm going to put my hydroxyl over here. Okay, so what is my product going to look like? Well, I want to count my carbons. I have 1, 2, 3, 4, 5. Let's start with that. 1, 2, 3, 4, 5. Now, attached to this 5th carbon, I have a methyl group. And what else do I have? My hydroxyl group, my OH. Now, I need to pick up and go 1, 2, 3 more carbons. So I'm going to go 1, 2, 3 more carbons. So count your carbons. 1, 2, 3, 4, 5, 6, 7, 8. Go back and check. 1, 2, 3, 4, 5, 6, 7, 8. And then I have 1 methyl group with my hydroxyl group.
So why is H on the right? I thought it liked to be with more hydrogen.
It does. It does, because if you looked at this, if I zoomed in on that carbon-carbon double bond, I would have this. Right? This one has, let's just call it an R group. Right? And it has a hydrogen because nothing's there. Then this one has an R group and an R group.
Okay.
So I'm going to stick something here and something here. So if I put a hydrogen here, it would be hydrogen, hydrogen, and then the hydroxyl here.
Okay, I got it.
Yeah, sometimes you just have to kind of,
I was thinking you look at all the rest of the stuff and find the hydrogen. Not all, just the one.
just the one.
Okay.
See, just look where the double bond is.
Just look where the double bond is. Right and the left of the double bond.
That's where I got from.
See, R group, R group. Here is R group, hydrogen. So hydrogen is going to stick with hydrogen.
Where did you get that R group on the left hand side?
This right here. Okay. All right, so how about this one? Here's our carbon-carbon double bond. One of these carbons, this one or this one, is going to get hydrogen and the other one's going to get hydroxyl. It doesn't matter. Because this is a symmetric molecule, it doesn't matter. So I can put my hydroxyl here, and then my hydrogen over here, or you could have done it the other way, because all you do is turn it, and it's the same molecule, right? So when you draw it, draw your house. Hopefully your house is not as sad as my house. Don't put any double bonds, and then give it 1 hydroxyl group. And honestly, it doesn't matter if you put it here, 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 or here. It's the same molecule. So that's kind of nice about it. Because it is a skeletal structure, and you never have to draw your hydrogens for a skeletal structure. Is that our last one? That is our last one. Woohoo, y'all did great. All right. So sections, chapter 6, sections 1, 2, and 3 before next Tuesday, but what do you have due? Homework tomorrow at 9 p.m. Homework tomorrow at 9 p.m. I know. And I know it's a challenge right now because there's no fall break. There's no, but stick with it. Do not give up. Please, please, please turn in those homeworks. Okay? All right, y'all have a great day. I'm going to try and restart this system to see if I can make this work. So does anybody have any questions on Zoom? I really want to shut down the computer and try and start it up again before the next class. So y'all need anything? Okay, I don't see any questions, so I'm going to go ahead and shut down so that I can try and get it rolling before the next class. If you need something, please send me an email.